most in your mind as far as difficulty for that exam. So I wanted to get you that ending material as soon as possible. As far as lab, next week is enthalpy. You're using your coffee cup calorimeter, you're using styrofoam cups. It is pretty straightforward, not too difficult, a little bit more involved in melting ice. Can't do this one at home in your kitchen. For a conversation I overheard yesterday, which was kind of fun. What was I going to say? It's the calculations that are difficult. And myself and the TAs this morning went through the slides for the lab, and we actually put together a slide, an example calculation slide. It'll give you a framework for all of your other calculations as far as for that lab. So make sure to ask your TA questions when they get to that slide. At a minimum, procedure sufficient to conduct the experiment. Yes, you're doing the entire thing. It is easily done in the allotted time. And your pre-lab assignment, at least attempted answers to those questions. You always have a week to actually correct your answers if needed. Quiz 10, you know what to say. Hopefully we're good with that. Exam 3, besides announcing that ending point of 11:20 of this month, 5:30 p.m., 60 minutes. Most students are going to lab 162. I did put the remainder of the lecture activity problems, actually not the remainder, as far as I thought we're going to get, and then some Moodle problems for electron configurations. Are there any questions you've thought of? I also, as usual, on Friday, I did open up the next week's module, and besides the enthalpy lab information, since the entire lab is being done, all that's there is to remind you about what you need to have done for your pre-lab work, but more importantly, the exam 3 review is there along with the answers for that review. In addition, even if you don't want to look at the review yet, you want to at least open it up to see that lab page because it tells you what given information you'll have, and that's going to be the same for the exam. Okay, so this way you know in advance what you'll be given. So I want to point that out. I remember the last couple exams I asked people, who's looked at it yet? And not many hands went up. This is how you know you're given information. Anything that's come to mind? All good? Yeah, I just did a view for you. And we're going to be using the PowerPoint a lot today, so I think I'm going to put that on the center screen just so that the one side of the class doesn't have to look at an individual little thing there. If we need to go back to the paper, we will. Okay. We're going to do a brief review of electron configurations, how they connect quantum numbers along with orbital diagrams. I say brief because we assume you have done some of this before. So in number 10, what are electron configurations? An electron configuration shows how the electrons are distributed amongst the sublevels. In this class, you're always doing a ground state electron configuration, although from that video, you should know what's meant by excited, right? You give electrons a little extra energy, they go to a higher energy level or energy sublevel. You'll always be writing for our ground state though. So they do have a little box there for you, and they want you to think about how these are determined and written. So I actually, you may have seen, just added the set of quantum numbers that they asked you for in that box. Set of quantum numbers for the ground state electron in hydrogen. Hydrogen element number 1, it has 1 electron. Therefore, that electron for the ground state would be the first energy level. Relax as much as possible. In the first energy level, we only have 1 allowed value for L, which is 0. And therefore, we only have 1 allowed value for M sub L. And it's typically traditional to do spin up first, so I did the plus 1/2. Electron configurations are abbreviations of that information. Actually, it's an abbreviation of an abbreviation. So our electron configuration does give us our principal quantum number, N, that's the 1 in front of the S. It does give us our L value of 0, as long as you remember that L of 0 means S. We are kind of have to think about a little bit about the ML value, need to know the rule to understand and remember that there's only 1 S orbital there, and we don't have the information about the spin in the electron configuration. 1s1 does not tell you it's spin up. It doesn't directly either tell you that there's only 1 S orbital, unless you remember that. The abbreviation that this is an abbreviation of is the number 11. Orbital diagrams are actually the first abbreviation for different representation of a set of quantum numbers. And so for our hydrogen's electron, the orbital diagram is not a Bohr diagram. We traditionally show it as boxes, although I was taught a line. I know some high school instructors do circles for the orbitals, which is fine, because I've seen it come through in exam 3. In this representation, we know that we're in the first energy level. We have the 1 by the S, so we have our N value. As long as we remember the transcription that S means L of 0, we have our L value. There is one box, which is telling us there's only one orbital. You still have to remember the rule to know that that would mean an N sub L of 0, but we are directly shown the spin by the arrow being up. Spin up, up arrow. If it was minus 1/2, it'd be a down arrow. That's my notes. Any questions before we have another example that's not in your lecture activity pages? What element is this? 1s2, 2s2, 2p1. Different way to figure it out. Anybody know? It's an atom. Oh, that's not an ion. What was that? I think I heard it softly. Boron. We have 2 electrons plus 2 electrons plus a 5th electron. If it's an atom, the number of electrons equals the number of protons. If we look at the periodic table, we see that that's boron. You may have also learned other methods of doing that, which we'll be talking about. Looking at the very end, the 2p1 also told me it was boron. We'll get to that point. As far as the electron, sorry, that's the electron configuration. The orbital diagram. I like to show this other example because the hydrogen, there's just one box there. Oh, I don't know what that means. Notice in our p sublevel, we know that there are 3 orbitals because there are 3 values for m sub L. I also included those values underneath the orbitals, although I don't make students at this level really do that, but it helps you identify that m sub L not only tells you the number of orbitals, 3 values, 3 orbitals for our p sublevel, but also it tells us specifically which orbital. So if we are looking at any one of these electrons, we can write a set of quantum numbers for each one. Does anybody want to do that? Want me to write a set of quantum numbers for one of those electrons? I saw some head shaking. Again, I will leave my paper. Some semesters, nobody wants to do that. Other semesters, some people want to do that. I have found, especially in exam 3, that students have a misconception that if you're thinking about a set of quantum numbers, you're just thinking about the atom, or you're thinking only about the electron at the end. Every electron has a set of quantum numbers. So I'm going to quickly do this in a slightly different representation. As I said, I was taught to do lines. You can also have circles, so they don't have to be boxes. If we wanted to do it for this electron on the end, which is what most students usually are thinking about, we know that it's in the 2nd energy level, so 2 for N. We know it's in a p sublevel, and in a p orbital, what's the value of L for p? 0, 1, 2, or 3? 1. 0 is S, p is 1. So we have a 1. Because we know specifically which orbital it's in, its m sub L value would be -1, and it's spin up, so +1/2. However, you could write such quantum numbers for all the other electrons as well. In this sublevel, we have 2 of them. One of them would be 1, 0, 0, +1/2. The other one would be 1, 0, 0, -1/2, because one's up spin and one's down spin. emphasize in this example that all the electrons have their own set of quantum numbers. Any questions before we go on? I'm going to go back to most of the rest of the lecture should be on the computer. So for number 12, for single electron species such as hydrogen atoms or helium ions, there are a couple others, what quantum numbers dictate the energy of the atomic orbitals? Only n. This would be a vertical orbital diagram for a single electron species. If it's the ground state, the electron's always at the bottom. But we could excite. We don't write them, but we do have to understand that that could happen. The reason is only n. Notice 2s and 2p are at the same energy, with your y-axis being energy. 3s, 3p, and 3d are all at the same energy. 4s, 4p, 4d, and 4f are all the same energy, which is why Bohr's theory worked for hydrogen, a single electron species. We were unaware at that point of these sublevels and orbitals and this and that, and you can almost, if you extend the little lines, you can almost see his orbits, right? They're really big, they almost look horizontal, you're zooming in, because all of our sublevels were at the same energy. Once we put more than one electron into a species, his theory broke down because we get a splitting of the energy level, or we get a broadening. You can think of these energy levels not as four orbits or lines, but almost like the skins on fruit. The broader, then think about a grapefruit or an orange skin versus the narrower, like an apple skin. There's this broadening of this, and you'll see what I mean in just a second. But for single electron species, Rydberg equation perfectly calculated what was observed experimentally for the wavelengths of the line spectrum. Any questions before we see what happens when we have more than one electron? What do we have more than one electron? Do electrons like each other? No, they're all negatively charged. So we're trying for things that don't like each other, near each other, and that ends up having repulsive effects. Now the repulsive effects at this level we described as shielding. In number 13, top of the next page. Shielding occurs when electrons in lower energy atomic orbitals end up reducing or blocking out some of the positive charge in the nucleus, meaning it reduces the electrostatic attraction between the protons in the nucleus and the electrons that are further out. So having electrons within, you probably know the term core electrons, the one on the outside, valence, feels less the positive charge, and that ends up really kind of messing up the orbital diagrams. We're going to look at what we call the N plus L rule, meaning our energy is now dictated not only by N, it's also dictated by L. If you look above your table, the energies of the sublevels vary by the N plus L rule, or the lower the value of N plus L results in a lower energy for the atomic orbital, therefore the sublevel. When the sum is equal to two different sublevels, then the atomic orbital within a sublevel with the lower value has a lower energy. We're completing the table for this N plus L rule. Now, N is just the number coming from our sublevel. L is transcribing from the letter to the L value. So all S's are zeros, all P's are ones, all D's are 2, etc. We then just simply add it together. When we add it together, we get a sequence of numbers, which actually is going to tell us the order of the sublevel in a multi-electron species. The lower the number, the lower the energy. When we have a tie, the one at the lower energy level goes first. So hopefully you'll see we'll have 1s, then 2s. We have a tie for 3, but 2 for 2p is lower, so we have 2p, then 3s. Notice we have a tie for 4. We have ties for 5, a couple ties for 5, some 6s and 7s and 8s. This ends up giving us a somewhat muddled arrangement. The beginning is basically the same as what we saw before. 1s, 2s, 2p, 3s, 3p, but 4s actually has been experimentally verified to have lower energy than 3d, meaning there's an overlapping of the energy levels. We then get 4p after 3d. 5s 4D, 5P, 6S, 4F. So this is what I mean by, think of the energy levels as skins almost, and there's some overlapping going on. This is probably an order that you kind of had to learn in the past, at least maybe up to like 4P or so. You never really have to learn it because it's always given to you on those things on the wall and the things in the back of quizzes or on exams. The periodic table will give us the order, which is really nice. The periodic table is arranged the way it is. So don't think you need to memorize that. We will, either today or Monday, talk about how to do that. Any questions? We get a muddling or mixing up of the sublevels because we have more than one electron and they repel each other. And they also shield other electrons from the nuclear charge. This also is shown here, at least to an extent. We can see now in the second energy level, the 2s and 2p are no longer at the same energy, meaning the value of L makes a difference. 3s, 3p, 3d, look at how much broader that is, a thicker skin. 4s, 4p, 4d, and guess where 4f is? It's off the chart. It's a much broader possible energies for those sublevels. The energy, again, depends on N and L put together. Some students don't like when I click that in, it's really busy, but other students do like it because you can see the differences in the L values for the 2s and the 2p, and that's causing a difference in the energy. Now again, this was originally all theory. Using ionization experiments, we have verified that this is correct. When we can't verify something is correct, then we kind of tweak our theory. You'll actually see some tweaks probably on Monday. Any questions? I do have a comparison slide that has just both of them next to each other. Since if you do have a single electron species and we only use ground state in this class, it would always, the electron would always be at 1s, and notice that it's the same energy over here. As soon as you add more electrons, you're using this one, so you just always use this one. You don't have to write them horizontally. You already saw some that, vertically, you already saw some that were horizontal. Any questions? Again, this is exactly why Bohr's model only worked for hydrogen. We're unaware of the fact that electrons weren't orbiting on nice circles around the nucleus. Did anybody in high school learn the grid method? You know what I mean when I say grid method? I don't know if they're teaching it anymore these days. That's kind of what I mean. Oops, I forgot it wasn't there. I'll put it back up. Come on. There we go. That's what I mean by the grid method. When you write out your sublevels, notice you're just doing them in order, 1s, 2s, 2p, 3s, 3p, 3d, but then you draw lines or arrows. And if you follow the arrows, it actually gives you the correct order. It works if you were taught that. I don't encourage it, and I don't want to spend the time writing it out, because I see so many students on exam 3 using the grid method, but you have to write it out yourself, and then you make a mistake, and you get the wrong order. Whereas the periodic table gives you the order. But if that's something you've been taught, I'm not trying to break what you know. If you're confident using it, it's perfectly fine. But yes, it is the order is consistent with using the grid method. You get the same order. So I'll leave that up for a second, so I'm not sure if anybody's copying it out. Any questions? If anybody didn't get that and they do want it, feel free to email me. We are going to go on to page 238. I'm actually going to leave this up for a couple minutes. What is Pauli's exclusion principle? Last time we talked about it being no two electrons can have the same set of quantum numbers, so we also talked a little bit about how that went back to the other definition you probably learned in the past. This extends to our orbitals. Since right here, we have these two ms values used, we cannot put another electron into that orbital because we'd be breaking Pauli's exclusion principle. Only two electrons are allowed in any atomic orbital. Meaning for 14A, what's the maximum number of electrons? And I know it says in each sublevel, but there's no number in front of the letter. It really bothers me. put the S. If you want to put a 1 there, it's fine. Or 2 or 3, doesn't matter. If you're in S sublevel, there's only one orbital, therefore there are 2 electrons. If you're in a P sublevel, there are 3 orbitals, therefore there are 6 electrons maximum. A D sublevel has 5 orbitals, therefore 10 electrons allowed. And for an F sublevel, there are 7 orbitals, therefore there are 14 electrons allowed. Let's talk about the T sublevel for a second. How many elements are there in the transition metals as you go across a row? We start at the top, SC over Z. 10. There are 10 electrons allowed in D sublevel. Guess what? The last electron we put into the electron configuration goes into a D sublevel. Even if you look at the inner transition metals, the ones that are underneath, there are 14 boxes across there, and the last electron you put into any of their electron configurations is in an F sublevel. Periodic table tells you it all. We'll talk more about it. We do have a couple of rules we need to go over. Hund's rule. Electrons will fill degenerate orbitals to yield the maximum number of unpaired spins. I'm going to need paper in just a second, so I'm not going to flip back and forth. Meaning 1 electron per orbital, and if needed, pair up. If you only have 2 electrons going to a 2p sublevel, we don't need to pair up. We know that they're going to be separated. This is also experimentally verified, which we might get to today. So let's just put 1 each, and then you pair up if needed. The Aufbau principle basically means, in general, always start at low energy. We always start filling at the 1s. Meaning for a ground state electron configuration, all electrons should be at the lowest possible energy. Now, for some elements we'll talk about on Monday, that doesn't always end up meaning everything's filled from the beginning. We have exceptions because we've learned our theory isn't perfect. Why do you always start at the beginning? Don't want to start at the end. In 17, they want you to fill the first 25 electrons using the orbital diagram to the right, following Pauli's exclusion principle and Hund's rule. What element is this? Anybody? Is this an atom? Anyone? Element 25? Oops, that's 3. I need a 4, I think. Yes. I need a 4D. 3D, sorry. That's why I gave you the hint again, it's an atom. And I know the periodic tables in this room are not the best. If it's an atom, the electrons equal to protons, so we're looking for element number 25, which is manganese. I knew when I was writing that out, I had to stop in D. It's a transition atom. And notice it's the 5th box over. So there's going to be 5 electrons in that 3D sublevel. If you kind of, after you practice, after you've gone through all of it, you get the hang of this, it's really all about the end. Now, everything else is going to get filled up to follow the Aufbau principle. If you just started at the beginning, only putting 2 electrons in each orbital, and just kept going until you were up to 25, you would get the same thing. Remembering 1 electron per orbital, then pair up. And you know what element is, the periodic table tells you where to stop. As far as the electron configuration for this, we're now transcribing from our orbital diagram. So manganese electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Please note you don't have to have an orbital diagram to do electron configuration. Any questions? I do know we, just a second ago, said we have experimental verification that Hund's rule is the right thing to do, and that's what we're moving on to on page 239 at the top. atoms of the element or ions of the element interact with magnetic fields. We have terms diamagnetic and paramagnetic. If we have a sample that is what we call paramagnetic, that means there's attraction to a magnetic field, which on the particle level tells us we have unpaired electrons. If we have a sample that is diamagnetic, that means it's repelled by a magnetic field, which on the particle level tells us that all electrons are paired up. Meaning if we know elements' magnetic interaction with magnetic fields, we can then verify at the particle level that we're doing things right. Let's go see where oxygen ends. Oxygen, it's in the second period. It's over here. It's the fourth box in right next to fluorine. That tells me it ends in 2p with 4 electrons. Meaning, actually I want the orbital diagram. There we go. There's my 1s, 2s, 2p, 1, 2, ooh, oh my gosh, and not 4. There we go. There's only 3 orbitals there. Ooh. We have a possibility of this or this. Which, given what I just said about Hund's rule, is wrong. Well, this, if this was true, with everything is all paired up here, that would tell us that oxygen should be diamagnetic. Following Hund's rule, with some of them unpaired, tells us that oxygen should be paramagnetic. Guess what oxygen is? It's paramagnetic. That tells us Hund's rule is kind of the way to go. It is doing things right. Sorry for accidentally putting 4 orbitals with a P. I think I have one more click on this. Yeah, it shows the orbital diagrams. Meaning, the elements that are diamagnetic are kind of easy to point out once you know the periodic table method. Everything in group 2 is diamagnetic. Everything's paired up. Everything in the transition metals at the end, zinc, cadmium, mercury, all paired up. Everything in the noble gases, all paired up. I'm looking at the clock. We're going to stop. I really want to get to on page 239. That's